So today we're going to briefly look at electrons in excited states. When an electron is not in a ground state, it is considered to be in an excited state. There's some principles that we're going to look at and then look at some orbital spin diagrams and determine what excited state we're in. In other words, what principle was violated in order for those electrons to go from the ground state or the lowest energy state to an excited state. So the first is the Aufbau principle, and we talked about this yesterday. Electrons enter orbitals of lowest energy first. In other words, they build from low energy to high energy. This is the filling order that we look at when we are looking at the electron configuration. So basically, if electrons are not being placed in the order of electron configuration, you are violating Aufbau principle. Hund's rule is another one we talked about yesterday, where electrons enter orbitals of equal energy one at a time with parallel spins. So this was the filling the bus rule, where electrons will go up, 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 and then down, down, down in a set of p orbitals on a p sublevel. It's an example of Hund's rule. And if there's a flip in spins where they're not parallel, or if we double up before we fill all the orbitals with one electron, then that's considered a Hund's rule violation. Pauli's exclusion principle basically says no two electrons can have the same four quantum numbers. How that translates in an orbital diagram would be two electrons in the same orbital having identical spins. We did not study quantum numbers this year because it's removed from the AP exam, but ultimately quantum numbers tell us the location of an electron down to which electron in a specific orbital we're dealing with. If you have a picture like this, both these electrons are on the same level, in the same sublevel, in the same orbital, and have the exact same spin. So this is not possible. This is not an excited state. This is an impossibility. So let's take a look now at some of these orbital diagrams and see if we can figure some stuff out. So here in this first example, we have an s orbital and a sublevel of p's, and we have an up-down, so the s looks good, and the p's look good. We have them placed up, up, up. So this is a ground state. This looks absolutely fine, and there is no violation. And this next one, you can see we're going from s to p again, but this time, if you notice, we have a p there that has a spin that isn't parallel to the other spins. We have an opposite spin. So this is an excited state. That electron is going to flip back at some point and release some light or some energy, and therefore this is a violation of some sort. And because it is a flip and they're not all up, 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 that would be a Hund's rule violation. Looking at this guy, we have two electrons there that are in the exact same location in space. They're in the same energy level, in the same sublevel, in the same orbital, and have the same spin. So not going to happen. So this is impossible. And this is a Pauli's exclusion principle. Not going to happen. All right, looking at this, we are going from an S to a D, which is possible. So this could be level 3 or above. Sorry, that would be a 4S, making this a 3D. So looking at this, we can see it's kind of the same as that second example, where we have a Hund's rule violation, and that spin is not the same as the other spin. So this is an excited state, and this is a Hund's rule violation. In this next one, that's jumping out at me. That, again, is impossible. We have two electrons with the same spin in the same orbital on the same sublevel on the same level. So this is Pauli's exclusion principle. Not going to happen. Okay, looking at this, this is kind of misleading. I don't want you to think that, oh, this is an excited state, because my first inclination was to say that as well. However, this would be an S and this would be a D, a level below. And I'm sure you're thinking, oh, you should have filled this S first. Well, yeah, this looks like an excited state, right? It looks like we should have filled this S first and then continued on with the Ds. But if you think back to yesterday's lecture, we were talking about the ground state for the copper and chromium families. Remember? So we had an empty orbital here, and we moved the s electron to that orbital to help alleviate those repelling forces and bring everything down to a lower energy. So I know this looks excited, but this is an exception here where this is the ground state, and this is specifically for the chromium family. And our last one, now this is an excited state. We should have filled this S before moving on to the P's. And again, I'm sure you're thinking, well, why can't you have had that electron here and it not be an excited state, just like the previous example? Well, in this example, we're going from an S to a P. And if you recall yesterday, I talked a little bit about how the energy between S's and D's is very, very minute, so an electron could readily transfer. However, the jump between the S and the P is like jumping through the Grand Canyon, so that's not going to happen. Therefore, in order for it to happen, some external energy needs to be applied, and this electron had to be really, really excited. So we're in an excited state, and this principle then is an Aufbau violation. We did not fill the orbitals from low to high. We did not fill an electron configuration filling order. And that's it. Those are excited states.